All right, yeah, welcome back again. So we're going to, under this section, we want to look at statistics and testing. All right, we have different kind of tests that we perform in statistics, especially in R. Okay, so we want to look at some of the testing today, and before we go into the practical section. Okay, and the first, I want to first understand what is called descriptive and inferential statistics. You can divide the test into two parts. You can say one part is descriptive, the other part is inferential. And what does it mean? Descriptive statistics describe the characteristics of the data set under study without generalizing beyond the analyzed data. Right? This includes measure of central tendency, such as mean, median, mode, measure of dispersion, such as range, variance, standard deviation. We have frequency distribution, histogram, frequency table, and we have graphical representation, we have box plots, bar plots, pie chart, and the rest of them. Statistics are descriptive in nature, but we also have inferential statistics, which allow researchers to draw conclusions and make predictions about the population when it is impractical or impossible to study the entire population directly. The help of inferential statistics can draw conclusion and prediction, particular sample data. All right, so looking at this graph and this image now, you see that this population, the sampling population is information that is under sampling, not yet finalized. So when we have a finalized a sample, we call it sample, right? When we have finalized sampling, we call it sample, right? So descriptive just does not go beyond that, beyond this level. All it does is to categorize the data, right, and summarize it. So, but in inferential, that infer part of the population, right? In population, that make inference of the population. That what it means. That is, from this population, based on this sample we taken from the population, can generalize, right? Can make some inferences. That's exactly what that is talking about. Then we under descriptive, like I said before, we have mean, the mean value of your data, which is the average value of the numbers, and we have the mode, which represents the most frequently occurring value in the data set, and median. When you sort data by size, the median is the value in the middle, right? So we also have a descriptive for spread and dispersion. We have maximum, minimum is for range, is when they are subtracted. We have variance, the average square deviation from the mean, and we have standard deviation, the average deviation around the mean. We have interquartile range of the middle 50% of the data, difference between first and third quarter. So when you say inferential now, we say that it tests whether the patterns that we observed in the sample are likely to be present in the broader population or just a product of chance, right? So if it's not if it's not significant, you can say it's just a chance. But if it is, then we can say that the pattern we observe in the sample, all right, is found is found likely to be present in the broader population. So testing statements about the population on the basis of some characteristics. Right, so also we can talk about a different kind of a test, which is parametric and non-parametrics. Parametrics as assumptions. We call it parametric test assumptions. All right. The first assumption is called normality. That is normal distribution from Gaussian. The sample data come from a population that approximately follows a normal distribution. The normal distribution I'm talking about is Gaussian-based normal distribution. All right. We have different kind of distribution. So this is Gaussian-based. So it has some form of a bell-shaped curve. I'm going to see examples later. So this is just the first assumption. It must be normal. So you can also further test this data using Shapiro test and the rest of them. But at least graphically speaking, you can see that this particular data is not normal. It's not normally distributed. All right. Or if it's normally distributed, you can see the shape of the data graphically. And also we have what they call homogeneity of variance. And this is talking about the sample that come from a population with the same variance. They have the same variance. This is very important before we can go further for any parametric test. And we have also test of independence. The sample data consists of independent observations and are sampled randomly. All right. So this is very important. You can also check this using chi-square possibly, and outliers need to be maintained at a minimal level. Sample data don't contain any extreme outliers. Yeah, I expect to have one or two outliers there, but it must not be too extreme. And of course, outlier can easily be handled easily. I mean, using different kind of tools, which we are going to see later. So we have parametric tests such as t-test. We have different kind of t-tests. These 5 types, but at least we look at only 3 types. Compares means. Okay, compare the mean of 2 groups. We have ANOVA, compare the means of more than 2 groups. When the group is more than 2, move on to the ANOVAs. Chi-square assesses whether there is a meaningful difference in the proportion of the various categories. And we have a chi-square of a set of independent as well, right? So apart from the proportion, which is also otherwise known as a goodness of fit. Okay, so we also have correlation, which assesses the relationship between 2 numerical variables. All right, and we have a regression, and as you allow us to predict the value of a variable, which is called dependent variable, based on the value of another variable called independent variable. So while one variable is held constant, we look at what happened to the other variable. So that is power of regression. We're going to be seeing an example of that later in R. Then we must understand that the parametric test is robust. Why that is what that means is that most times our data is not always perfect. Yes, don't you cannot rely too much on data. I think that the new data will be very perfect after you have finished gathering them together and everything is fine. No. Data is not always perfect. So that is why it's not all parametric test assumption that will be met. So, but not all parametric tests should be violated. Okay, parametric test is robust because and that's the good news. Even if normality assumption is violated, you can still use parametric procedures. That's what it means. Especially when you have a large sample size, okay, and you have an equal group size. Maybe your one of your column of your categorical data you have maybe gender and a male 50, female 50, total of 100 observations. That is very good because you have an equal sample size for groups. So it's very powerful. It's like make your work very, very perfect. So you can go ahead and say use a parametric test, even though all the assumptions are not met. All right. However, we must be aware of multiple violations. Therefore, so when the assumptions are too badly violated, then we now use what we call non-parametric. Okay. But the parametric test can still be used when part of the assumptions are not in order, are not met. Then you can still use parametric tests. Okay. So we have different kind of parametric text based on the data that we have. People ask questions, what kind of test will I use for my data? No. It depends on the kind of question you have. Your question determines the type of test you use. Meanwhile, in this particular course, we are going to show you different kind of variables that you have in your data, because the kind of question you are going to answer, it also depends on the kind of variables you have in your data set. All right. So based on those variables you have, we are going to see the kind of test you can perform. So but your test will perform based on your exact questions, question you're trying to answer. Okay. Somebody will tell you that you must use this, you must use it. No. Based on the question you are about to work on, then look at the variables you have in your data set. Are they sufficient to perform one test or the other? If you have them, no problem. Then you can go ahead. So we'll be showing you different kind of variables when they are available. When this is available, you use this test. You use this test. You have this. You do the test. That is how you learn. Then when you now have questions you want to address in your research, then you can now look at the variables. Does variable fall into this particular line? Then you can test. So not that people will just say, okay, before you have this question, you must use this. No. Your variable is very important. Okay, you must know the variables you have in your. That's why you have to explore your data properly and understand it. Okay, so when you have uh, one categorical variable, for example, you use chi-square for one sample proportion. That's what it means. It's called test of goodness of fit, right? So that is you are directly dealing with categorical data this time and not numerical data, right? That is a chi-square. You can also do chi-square for two categorical variables. Maybe you have two categorical variables in your data. Now, yes, you can do chi-square. Uh, that's test of independence. So the independent can one particular data value be predicted based on the value of the other? Are they dependent on each other? So you have to, that is called test of independence. So under that is chi-square. Chi-square is good for both parametric and non-parametric because it's not actually testing on numerical data. It's testing on categorical data. And both parametric and non-parametric are both have categorical data. So it's not really testing, and it's not actually based on parametric test assumptions. Okay, so because it's not numeric, it's just a categorical data. Even though it could be numbers, sometimes does not make it numerical data. It is just a categorical data. So take note of that. And you have one sample t-test. Okay, when you have one sample, you can use a simple t-test. And if you have two independent samples, you can use unpair. We do the testing on pair sample t-test. If you have two dependent samples, we have paired sample t-test. If you have more than two independent samples, we have what they call one-way ANOVA. If you have more than two dependent samples, we do one-way repeated ANOVA. And we have between two numerical variables, we can do Pearson correlation. So, and the same thing follow for non-parametric test, parametric counterpart. Okay, same thing for simple test. We have constant test for one sample, right? For we have Whitney U test for unpair. U means unpaired test here. That is in replacement with a parametric. Then we also have a pair sample. Say we have one person sign ranked test for pair sample test. We also have Kruskal-Wallis for one-way ANOVA. We have Friedman ANOVA for two-way ANOVA or for one-way repeated ANOVA. And we have Spearman correlation in replacement with a Pearson correlation for parameter. So when this one fails, you can just switch to this. So that's what it means. All right, so is lost. Okay, we'll be seeing the both how to test this. We are going to work on individually one by one later. Then before you go to this and see this one later. So we're going to do them one by one as we go. So before we go further, we have to understand what is hypothesis. Because that will help you to understand your research questions. For testing a claim about a parameter in a population using data measured in a sample, that's a hypothesis. So we can develop a question. If you don't have one, you can come up with one yourself. For example, does eating late at night really cause stomach protrusion? That's a question. But because of this question, now we have to develop a hypothesis now. We have a null hypothesis, we have alternative hypothesis. Okay, the null now what we're actually looking at is alternative. Actually, that's what we are looking at. We are looking at we are saying that the eating late at night does not cause stomach protrusion. It's not causes. Okay, so but we have to set it to it causes which is our null. Okay, if what you are looking at is that it cost it, then you have to set your alternative your null to it does not cause it. Okay, that just it will happen the other way around. Okay, but the alternative is the main thing that we are trying to address. This alternative, that is our predictive answer. Okay, when this one fail, we can now reject alternative. Okay, it's only when this one fail. But this is our focus. We are trying to say that eating late at night does not cause stomach protrusion. That is what we're trying to say. But if our test now fails, we can now reject alternative and say, okay, because the one fail, we can now say, okay, let's go with eating late at night does cause stomach protrusion. So we can now partially, similarly agree with this. Okay, but this is what we are focusing on. So that is called hypothesis. So we are going to be seeing a various example of that later as we go on. then you understand that they are what they call confidence level, which is a probability that the confidence interval actually does contain the population parameter, assuming that the estimate process is repeated a large number of times. So we have the what is called significant level, which is known as the p-value. So p-value being probability value of an estimate. So commonly we have heard p-value, p-value, p-value simply means probability value. Right? So and this probability value it depends on the threshold you choose for your research, for your work, right? So it shows that if a p is less than a predetermined threshold, the result is considered statistically significant. That's what it means, which means we have enough evidence to reject the null hypothesis in the favor of alternative. That's what it means. So we have confidence level 90, we have 95, we have 99. Common one is 90. So 90 is a common usually used confidence level. All right, and we are which will automatically give us a 0.05 significant level. All right. So, but if your work is more stringent, you can use maybe 99%. Okay, depends. All right, but this is a common one, the 95, and we usually see this every time in every research work. That is the standard. All right. So, so we'll be seeing this, for example, anytime we work on this, and then we at 90% confidence level. That is if that's what you choose. If p value is less than 10%, which is 0.01, then you have to reject a alternative null hypothesis. But at the confidence level of 95, if p value is less than 5%, that's what it means, then reject a null hypothesis. At 99% confidence level, if p value is less than 1%, reject it's not. It's a one terminology we do not reject the null hypothesis use. We don't say we do not accept. We accept. No, we say we do not reject. Not that we accept. If you reject null hypothesis, what happens to the valid hypothesis? Do you accept it? No, you don't accept it. You say you do not reject it. You don't accept it. The reason is simply because we typically cannot definitely prove that the null hypothesis is used. Right? I mean, it's true. Okay, cannot prove it because there might be still be some other factors or limitations that prevent us from making a definitive conclusion. So you don't say we accept it. You know, it's ongoing research works. All right. So we do not accept. We do not reject that one. That what we say. Then we now say that we reject this. We do not reject this. That is that we continue from there to practical section. So thank you so much for listening, and you can post your questions if you have anyone in the comment section, and I'll see you in the next class, in the practical class. Thank you so much.